All right, everybody, let's talk electromagnetic induction. Okay, so how do we produce a current in a wire? Now remember that a moving charge in a magnetic field will receive a force based on our right hand or left hand rule, depending on whether it's positive or negative. Now imagine a wire that's sitting in a magnetic field, and we just take that wire and we move it along. Okay, when we do that, remember that the wire has protons and electrons inside. So as we move the wire through the magnetic field, it's going to, well, the protons and the electrons in the wire will receive a force in opposite directions based on the right hand and the left hand rule. So protons will be pushed, in our picture here, to the top, and electrons will be pushed to the bottom. Now this produces a charge separation, an EMF, or a voltage, just like a battery. Okay, so if we hook this thing up to a light bulb, the light bulb will light up. All right, so here are our equations for it. So here is our wire that's moving through the magnetic field to the right. Based on our right-hand rule, make sure you check this, the protons or positive charges get pushed to the top end, and the electrons would get pushed to the bottom end. I only drawn a proton or a positive charge. Now we know the protons don't really move, but the same thing is in effect. Positive charge will be at the top, negative charge will be at the bottom. We get a charge separation, an EMF, or a delta V, or a voltage from this. And our equation for it is EMF equals BLV. Now I'm going to go through that a little bit later, how that comes about. But B is the magnetic field strength in Tesla. L is the length of the wire and the magnetic field that are embedded together. So in this particular picture, notice I have the length only for the magnetic field because the wire extends beyond the magnetic field. So it's only where they are together where the wire is moving through the magnetic field. And V is the velocity of the wire. So cool. So we could do this and we could cause electricity to flow. Nice. As long as we keep the wire moving through the magnetic field. As soon as we stop, all bets are off. No more EMF. But there's another way to produce this. In fact, this is just a subset of the overall way to produce electricity in a wire, and we need to talk about flux. So what is magnetic flux? So first, flux in general is any vector that passes through an area. Okay, I'm going to draw an arrow here passing through, or lots of them passing through. The more area there is, the more flux there'll be. Or the more arrows there are, the more flux there'll be. So more vectors, more area, more flux. And you get maximum flux when they pass straight through. You get less flux when they pass through, say, at an angle instead of straight through. They pass through at an angle. And when they go by, they don't produce any flux at all. So like in this picture on the bottom right, there's no flux when they pass by the area. So here's our equation for magnetic flux. So we have the B vector, the magnetic field vector, and an area and a cosine theta. So magnetic flux is in Tesla meters squared, which is given a name of Webers, WBs. B is the magnetic field strength in Teslas, and A is the area in meters squared. Now, remember, it's the overlap of the area and the magnetic field. So if this is my area and I only have a magnetic field covering half of it, I only do that half of the area that is covered. So they have to be overlapping. And B is the angle, theta is the angle between the magnetic field and the area. So that's a little weird. So we do have this vector for the area. The area vector points perpendicular to the surface. That's my area vector right there, this yellow area, and it's perpendicular. So you can see that when they are in opposite directions or in the same direction, cosine of 0 or 180 is 1, or absolute value is 1. So you get maximum flux. When that's perpendicular to each other, like we see here, then the cosine of theta is 0, and we get 0 flux because we have a 90-degree angle between the two. So now, Faraday's law. So if we can change this magnetic flux with time, will produce an EMF or a delta V, or essentially a battery, right? We need to change the flux with time. So that's the change in magnetic field strength, and or change in area, and or change in angle with time, and will produce an EMF. So Change magnetic field, change the area, change the orientation angle theta between the magnetic field and the loop. All right? Any of these methods will produce EMF. So here's practice. A wire loop sits in a magnetic field directed into the page. So here's our X's for the magnetic field. Okay, describe 3 ways that we could change the magnetic flux and produce an EMF and electric current in the wire. There's actually lots and lots of ways to do this. I could take the loop and move it completely out of the magnetic field, and I would have a change in flux. So I'd have flux, and then I'd go to no flux. So that would work. I could take the loop and I could change the area of it by smashing it flat and then opening it up and then smashing it flat. That would change the area. That'll work. I could change the strength of the magnetic field somehow, like make the magnetic field stronger or weaker. That would work. If I could rotate it or change its orientation, and this is the way that turns out that is the easiest usually, is you take it and you just rotate it in the magnetic field. So you go from maximum flux to 0 flux to maximum flux. All right, so here's a couple of questions for practice. We have 3 diagrams. Diagram for A, B, and C. Okay, which of these will be producing an EMF and thereby producing current in the loop of wire? So A and B have this loop of wire and a magnet. In A, we're rotating the magnet about its vertical axis. In B, we're moving the magnet away. And in C, we have a magnetic field and we're moving the loop through the magnetic field. Which of these will produce a change in flux? Well, A won't, because if I take a magnet and I have it above a loop and I just rotate it like this, the magnetic field lines are still going through that loop, same strength. So no change in flux, no EMF. B, if I take it and I move it away, okay, well then we're talking. We've got a change in flux because the magnetic field lines were going through and now they're not. So that would produce an EMF and current. How about moving that loop through a uniform magnetic field? Well, we have flux, but it's not changing. So again, no EMF, no current for C. So only B will work. On the test, they're most likely to ask you questions about when there's flux and when there's not. However, if they do ask you numerical questions, then just plug your numbers into the equation. Just find your flux at the beginning and at the end and subtract them. Your change in flux with time will give you what your EMF is. Lenz's law. So the direction of the induced current opposes the change in flux, is what Lenz said. The EMF that is produced in the wire creates a current. That current, remember, will produce a magnetic field. So whenever we have a loop of wire with current in it, it produces a magnetic field, right? Remember the solenoid rule? And that magnetic field has to oppose the change in the flux. So there's an existing amount of flux, it's changing. The induced magnetic field from the loop will create a magnetic field that opposes the flux change. All right? So the induced B field is trying to keep the flux constant. So here's some questions you can ask yourself to help you solve these problems, to figure out what direction the current is going to go. First, always ask yourself, is there magnetic flux? Second, ask yourself if the flux is changing. If either of these is no, then quit. There's no current and there's no EMF. Now, if you say that it's changing, then how is it changing? Is it increasing or decreasing, and what's its direction? That'll tell us how we can oppose that change, and then once we know what kind of magnetic field we need to oppose the changing flux, then that'll tell us with our right-hand rule for a solenoid which way the current is flowing. So let's practice. So here is a stationary loop outside of a magnetic field. First question, is there flux? No. Stop, move on. Okay, next one. What if we have a moving loop, but it's outside the magnetic field? First question, is there flux? No. So no current. All right, how about this? Now we have a stationary loop inside of a magnetic field. So it's sitting in here and it's stationary. Is there flux? Yes, there is, because there's magnetic field lines pointing out of the page through the loop. But is it changing? No. So no induced current. How about if it's moving in a magnetic field? That's a uniform magnetic field. Well, there's flux, but again, it's not changing. It's staying the same because the same number of magnetic field lines are passing through there as it moves through the field. Let's get ourselves some induced current here. So here's one where the loop is entering the magnetic field. Now I want you to notice that the magnetic field ends right here. So this front part of the loop is starting to receive flux, and as it moves to the right, it's receiving more and more flux because more and more area is being embedded in the magnetic field. So is there flux? Yes. Is there a change in flux? Yes. How is it changing? Well, the magnetic field is coming out of the page and it's increasing. Okay, so our change is that it's out of the page and increasing. So what do we need to oppose that? We need a magnetic field that's into the page to oppose the increasing out of the page. So the magnetic field that will be produced by this loop will be into the page to oppose the changing, strengthening magnetic flux out of the page. And which way will the current then be in that loop? Well, if you use your solenoid rule, you can see that it has to be clockwise to produce a magnetic field into the page. All right, you got it? Let's try it again. Okay, here's one. We've got a loop of wire that's exiting a region of magnetic field. So here's our magnetic field. It's exiting the field. So do we have flux? Yes. Do we have a change in flux? Yes, because it's out of the page and it's decreasing because less and less area is being covered by this magnetic field. So it's out of the page but decreasing. So we don't want it to decrease. So we don't want this out of the page to decrease. So we need more out of the page magnetic field to try and keep it the same. So this loop will get a current that is counterclockwise to produce a magnetic field out of the page to try and oppose the change. Again, in a problem like this, if they give you numbers, just plug it into the equation and find out the flux at the beginning and at the end, and that change in flux with time will give you what your EMF is, or at least the average EMF. Here's another example. We have a magnet that's moving towards a loop of wire as shown in the figures. So here I have a north-south magnet. It's moving to the left towards this loop of wire. Notice I've tried to draw it 3D. So the magnet is going to pass through the loop. This is the front end of the loop. This is the loop behind the magnetic field lines. And I've drawn the magnetic field that comes out of the north end of a magnet. So is there induced current in the loop? And if so, what direction is it? You pause the video, see if you can figure this out. All right, let's go through it together. Is there a magnetic flux? Yes. Is there a changing flux? Yes. Well, how is it changing? Well, the flux from this magnet is to the left through the loop. And as we get this magnet closer and closer, it's increasing in strength to the left. So we have flux to the left that's increasing. So we want to get rid of that increasing flux as best as we can. So the loop will induce a magnetic field to the right to oppose the increasing flux to the left. So which way does that mean current flows in this loop? So it's a three-dimensional thing represented in two-dimensional picture, so it's a little hard. But current would come out of the loop here and into the loop at the bottom so that it would go and produce a magnetic field to the right. Okay? Now, question for you. What if we cut this loop so it wasn't complete? What would happen then? We could still produce an EMF in the loop, but there wouldn't be current, right? No current would flow because it's a disconnected circuit. It's like a switch that will be opened, right? So no current through the loop. So this time I have a north-south magnet moving to the right. I'd like for you to pause the video and determine which way the current will be passing or going through this loop. All right, ready, set, pause the video. Okay, let's go through it together. So is there flux? Yes. The magnet this is the south end of the magnet, so magnetic field lines will be passing to the right through the loop. So we have flux, and it is changing because as we move the magnet away, the magnetic field strength will be decreasing in strength. So our flux is to the right, but decreasing. So we don't want it to decrease. We want it to stay the same. So the loop will produce a magnetic field to the right to help support the decreasing flux to the right. That means, hey, the current's going in the same direction as last time. All right, so here's some practice problems for you. In question 4 and 5, we got a square loop of wire that's pulled through a magnetic field at a constant velocity as shown in the figure. At which locations is current produced? Explain. And where there is current, what will the direction be? All right, pause the video, see if you can figure this out on your own, and then we'll go through it together. At 1 and 5, there's no flux, so no current. At 3, there's flux, but it's not changing, so no current. At 2, it's moving into the field, so we have a flux into the loop, the square loop this time. We have flux into the loop, but it's increasing. So we want to oppose the increase. So we need a magnetic field that's out of the loop, up out of the page. So that would be a counterclockwise current through the loop. And then in, what would that be, 4, it's moving out of the magnetic field. As it moves out of the magnetic field, it has magnetic flux into the page, and it's decreasing. So we don't want the into the page that's decreasing to decrease. We want it to stay the same. So we want more magnetic field into the page to help support the decreasing into the page flux. One more. In this particular one, we have a resistor and a couple of wires, and then we have a bar here that we're sliding to the right. The distance between these wires is Y. The distance between the resistor and this bar is X, and here's the magnetic field, and we're pushing or pulling this thing to the right with a velocity. Explain why current is produced in the loop, and which direction does the current flow through the resistor. So pause the video, see if you can answer these questions, and then we'll go through it together. Did you pause the video? So there's a couple of ways to describe why there's current in the loop. You could say that I'm pulling this bar through the magnetic field, and so the magnetic field is out of the page, and the protons in the bar are moving to the right. So out of the page, moving to the right, so the protons would be pushed downward and then around the loop. Okay, so they're pushed downward in the bar and then around the loop. So counterclockwise. So that'll work. Or you could say, well, we have a change in flux. So as I pull this bar to the right, we have an increasing outward flux out of the page. So this loop will produce a magnetic field that will be into the page to oppose the outward increasing flux. And that also would be clockwise. So either way you want to describe that, you'll get the same answer. I just wanted to say a couple things. Where does this equation come from? So this is BA cosine theta divided by time is our change in flux. Now, we have a cosine of 0 here, so this turns out to be 1, so that goes away. So we're left with BA over delta T for this particular setup. Now, the magnetic field is not changing, okay? But what's changing is the area. The area is this Y times this change in X, how much X is changing. So it's Y times change in X divided by time. So Y is a constant, but X is changing. So change in X over time is the velocity. So what we end up with is that this length right here, Y, times the velocity of this bar will equal the change in area over time. That's where this BLV comes from. So please be careful. This L is the Y dimension here. It's the length of the bar. It is not this X, all right? Because that X is changing, and that's taken into account in the velocity. By the way, which end of the bar becomes positive? So remember, as we move this to the right, protons will be pushed downward, and so this is the positive end of the bar, and this would be the negative. Electric generators and motors. This is how we generate electricity in the United States. We have a bunch of loops of wire, and we have a bunch of magnets, and then we force them to rotate past each other. Turns out to be really efficient to do that. So we have some way of making that thing rotate past there, and electricity comes out. Nice. Now a motor is the exact same machine in essence. It's just in reverse. When we shove electricity into these loops, they produce a magnetic field which will repel the magnets that are inside here, force it to turn, and that'll turn this shaft. And then you can make that shaft do whatever you want. You can have it connect to tires, say, on a car, and you have an electric car. So how do we get this to rotate? Well, in the United States and across the world, there are several ways. We can burn coal. We burn coal to boil water, to create steam, and we make that steam push a turbine, which moves loops of wire past magnets, which generates electricity. Or we can split atoms, which generates heat, where we can boil water, which would create steam to turn a turbine, to turn wires past magnets, electricity. Or we could build a big lake and then have the water flow down, turn a turbine, which turns magnets and wires past each other, which generates electricity. Or we could have wind, turn a turbine, and then that rotates magnets past loops of wires, and we generate electricity. You notice it's all the same, right? So almost all the electricity in the world is generated this way. So this is huge, huge idea. So the next time electricity goes out in your house, I want you to remember Faraday's law and how important it is and how it's changed the way the world is. It was only 150 years ago or so that this idea was generated or invented. And then it's only been about 100 years since half the houses in America have had electricity. So it's really not been that long ago. All right, another example of where we use this idea of induction. So a speaker and a microphone. So a microphone is nothing more than a coil of wire that's wrapped around a magnet, and it's on a flexible membrane so that it can vibrate when sound waves hit it. So the sound waves hit this, the loops of wire oscillate back and forth past this magnet. And when they do, there's a change in flux, which generates electricity. Now, since it's oscillating back and forth, it generates electricity one way and then back the other way, one way and back the other way. So the electricity coming through these wires is oscillating. We take that and we can record it and then play it back later. Or we can send it through an amplifier to a speaker. And so that oscillating electric current goes into this coil right here, this red thing. And that's a loop. So that's a solenoid. So that generates a magnetic field, an oscillating magnetic field. And there is an external magnet right here. You can see it's cut, this big loop of magnet here. So that interior loop is a magnetic field in an exterior magnetic field. And so it vibrates up and down. And that drives this cone, which drives air, which makes sound that we hear. So a microphone and a speaker are really the reverse idea of each other as well. All right, everybody, that's it. That's induction. Good luck on the test. You're going to do great. Bye.